Welcome to the course on 3G and 4G wireless mobile communications. So, the title of the course that we are going to talk about is 3G and 4G wireless mobile communication systems. Wireless communication systems have become an integral part of our lives, especially during the last decade. 3G stands for third generation wireless communication systems, and 4G similarly stands for fourth generation wireless communication systems. So, this course is about 3G and 4G wireless communication systems, that is third generation and fourth generation wireless communication systems. To get a better idea of what 2G, 3G and 4G systems are, let us start with a brief description of the current second generation systems, so that we understand the nature of the current second generation systems that we are using and the upcoming, and then we can proceed on to learn more about the upcoming third generation wireless systems and fourth generation wireless systems. So, let me start with a brief introduction to different 2G wireless systems and 2G wireless standards that are currently being used. So, let us start with 2G wireless systems. Let me make a table here, and in this table I am going to write the different standards and the data rates of the different standards. The first 2G wireless standard is currently the standard which most of you must be familiar with, that is the GSM standard or the global system for mobile communications. This is the most popular 2G wireless standard that is currently in use. This has a basic voice data rate, digital voice data rate of 10 kilobits per second. That is, when I say about a voice data rate, I am talking about the voice call that you place from one GSM mobile phone to another GSM mobile phone, that has a data rate of approximately 10 kilobits per second. This is not the only second generation wireless standard that exists. There is another competing second generation wireless standard, which is CDMA. It stands for code division for multiple access, and that also has a voice data rate of 10 kilobits per second. Later, there were intermediate 2.5G or 2.5 generation standards that were developed to enable internet access, or what is technically known as accessing best effort packet data over cellular networks. These standards are the 2.5G or 2.5 generation standards. The first is GPRS, which is General Packet Radio Service, and that has a data rate of around approximately 50 kilobits per second to access packet data, or essentially to access internet over your GSM mobile phones. And another competing 2.5G, or sometimes also known as a 2.75G standard, is the EDGE standard or enhanced data for GSM evolution. I will write again these acronyms separately, so that to give you an idea of, to explicitly state what each of these acronyms here stands for. EDGE is essentially has a data rate approximately 200 kilobits per second. Alright, these constitute basically the broad family of 2G, that is second generation, and 2.5G standards. Let me give you a list of these acronyms for more clarity. This is GSM, is the 2G standard, that stands for Global System for Mobile Communications GSM stands for Global System for Mobile Communications. CDMA stands for Code Division for Multiple Access. GPRS stands for General Packet Radio Service. GPRS stands for General Packet Radio Service, and EDGE, which is the other 2.5G or 2.75G standard that I briefly mentioned, stands for Enhanced Data for GSM Evolution. That is, EDGE stands for Enhanced Data for GSM Evolution. This is the family of (2G) slash 2.5G slash sometimes also known as 2.75G wireless communication standards. All right, I will simply call this as standards. All right. So, this is the family, that is GSM, CDMA, GPRS, EDGE. These are the family of 2.5G, 2.2G, 2.5G wireless communication standards, enable to place voice calls from mobile to mobile, also some basic internet access, packet data access over cellular networks. As we all also know that we are progressively moving towards third generation and fourth generation wireless systems, essentially because of the rapid popularity of wireless systems, rapid popularity that the 2G wireless systems have gained. There has been a tremendous demand for increase in the data rates to support not only voice calls, but also video related applications such as video calls, video conferencing and so on over future wireless systems. This has led to the development, this has led to the desire to have high bandwidth over existing cellular networks, that is to run applications of high bandwidth over existing cellular networks, and that has led to the development of 3G standards and also 4G wireless standards. So, let us start looking, let me just give you a basic idea of the third generation family of wireless standards. So, let me describe the third generation wireless standards. I will again make a table to give you the name of the standard and its data rate, so that it will give you a better idea. So, let me make a table here. The first standard that I am going to talk about, the 3G standard, is the very popular WCDMA, also known as UMTS. WCDMA stands for wideband CDMA and UMTS stands for Universal Mobile Telecommunication Standard. I am going to give these acronyms again separately. Let me just briefly talk about the data rates of this standard. WCDMA has a data rate around 384 kilobits per second. As you can see, this has a higher data rate compared to GSM and GPRS, which are data rates around 10 kilobits per second for voice call to 50 kilobits per second for packet or internet access. Another competing 3G standard is CDMA 2000. This also has a data rate of 384 kilobits per second. There are also a set of 3.5G standards, which the first such standard is HSDPA/HSUPA, where HSDPA stands for high speed downlink packet access, HSUPA stands for high speed uplink packet access, and these have data rates that are roughly of the order of 5 to 30 megabits per second. As you can see, this has a drastically high data rate compared to previous 3G and 2G standards. Another family of competing 3G standards for high speed data access especially are the 1X EVDO group of standards, 1X EVDO, 1X EVDO Rev A, B, C. Rev stands for revision, that is 1X EVDO, and then subsequent modifications denoted as Rev A, revision A, revision B, revision C, and these are also capable of data rates around 5 to 30 Mbps. So, there are 4, similar to what we had in 2G, we have a set of competing a set of 4 competing standards: WCDMA, CDMA 2000, HSDPA and 1X EVDO. This is the family, or this is the family of the most popular 3G wireless standards. Let me give you again a list of acronyms for your reference. WCDMA, we have already seen that CDMA stands for code division for multiple access. WCDMA stands for wideband. CDMA, or essentially wideband code division for multiple access. UMTS stands for universal mobile telecommunication standard, that is UMTS stands for Universal Mobile Telecommunication Standard, alright. And CDMA 2000 obviously stands for code division multiple access. 2000 is the year roughly in which it was introduced. HSDPA stands for high speed downlink packet access. HSDPA stands for high speed downlink packet access. Similarly, HSUPA stands for high speed uplink packet access. In any mobile communication system or any wireless cellular network, there are 2 directions in which communication can take place. One is from the base station to the mobile, that is known as the downlink. The other is the mobile to the base station, that is known as the uplink. So, HSDPA is the high speed downlink packet access, HSUPA is corresponding standard for the uplink, which is the high speed uplink packet access. Alright, and also we talked about 1X EVDO, where EVDO stands for evolution data optimized. Alright. So, this is the set of 3G or third generation wireless standards. So, this is the family of 3G / 3.5G wireless standards. Alright, these are the 4 competing 3G, 3.5G wireless standards. Alright. So, we wish to understand these systems in better throughout this course, or one of the aims of this course is understand the fundamentals that make the deployment and design of such 3G systems possible. And of course, this has also led the desire for more bandwidth has not stopped there. This has led to desire for more bandwidth, and that has led to the development of 4G wireless communication systems and 4G wireless standards. Let me start with a brief description of those. 4G wireless systems, 4G stands for 4th generation. Let me again make a table, and since many of them here are still in the development stage, this table here is not very big. There are essentially 2 dominant 4G wireless or 4th generation wireless communication standards. The first one is LTE, it stands for long term evolution, that has a data rate of 100 to 200 Mbps, and there is another competing 4G standard which is WiMAX, which stands for worldwide interoperability for microwave access, also has a data rate of approximately 100 to 200 megabits per second. So, these are the 2 most popular or dominant 4G wireless standards currently in development and deployment in different countries in the world. So, again similar to what we have done before, let me just briefly write down these acronyms for your reference. LTE stands for long term evolution, and WiMAX stands for world wide interoperability for microwave access. All right, this is the family of 4G standards or 4th generation wireless standards. This is the family of 4th generation wireless standards. So, to briefly recap, we have 2G, 2.5G, 3G, 3.5G and 4G wireless systems. These are roughly around, let us say, 10 to 100 kbps. These are around, let us say, 300 kbps to even 30 mbps, that is 300 kilobits per second to 30 megabits per second, and 4G systems which are around 100 megabits per second to 200 megabits per second. And as you can see, the data rate increases progressively, and while this can support, while 2G are typically voice plus some basic data, 3G can support voice, data and real time video such as video calling, video conferencing, etc. Video calling, video conferencing, etc. And 4G can support a lot more applications such as voice, data, inclusive of these applications it can support online gaming, real time TV, in fact HD TV, high definition TV and so on and so forth. So, as you see, the result as the result of the increasing demand for higher bandwidth applications has led to the progressive development of 3G, 3.5G and 4G wireless communication systems. And in this course, we are going to the main motivation of this course is to understand the technologies, the underlying wireless technologies that have made possible the development of such 3G, 3.5G and 4G systems. Alright. So, let me start by describing a basic outline of the course, so that it will give you a roadmap or where we intend to go to. We will first start with a description. So, this is an outline of the course. We first start with our first chapter, which is basically wireless communications and diversity. The first chapter is wireless communications and diversity. The complete outline, including all the subtopics that we cover in each topic is given on the website. So, if you want more details, please go to the website. Here I will just describe the major sections that we will cover in the course. The first major section is wireless communications, a general introduction, and diversity, which is a key feature of every 3G and 4G wireless communication system. Then we are going to look in detail into modeling of a broadband wireless communication channel. Since we are talking about wireless communication systems, the wireless communication channel has a key effect on the wireless communication systems, because the wireless communication channel represents a very adverse environment, as we are going to see in the future lectures. So, we will devote sufficient amount of time to understand the nature of the broadband wireless communication channel. Then we will start discussing the key technologies that make possible 3G and 4G wireless communication channel systems, or in other words, those technologies on which, or those principles on which third generation 3.5G, 3.5 fifth generation and fourth generation wireless communication systems are built. So, the first technology is not surprisingly CDMA, which also stands for Code Division for multiple access. This is the first technology that we are going to look at. Another key technology which makes possible 3G and 4G wireless systems is a very key technology known as OFDM. This is the basis for all fourth generation wireless communication systems. It stands for orthogonal frequency division multiplexing. So, the fourth topic that we are going to look at in detail is OFDM, orthogonal frequency division multiplexing, is a key technology for all fourth generation wireless communication systems. And the fifth topic we are going to look at is another very important technology for 3G and 4G wireless communication systems, that is MIMO, or multiple input, multiple output communication systems. So, MIMO stands for multiple input, multiple output communication systems. These are an integral part of all 3G, 3.5G and 4G communication systems. So, we are going to spend sufficient amount of time understanding multiple input, multiple output wireless communication systems. We are also going to talk about UWB, which is a promising technology, which is ultra wide band systems. UWG stands for ultra wide band systems. And finally, we are going to look at the 3G and 4G standards actually, that is going to talk about 3G, 4G standards, that is how do all these technologies come together to define the 3G, 4G standards that have been proposed, such as WCDMA, HSDPA, LTE, WiMAX, and so on. So, in brief, this is the outline of the course. This is the path that we are going to follow. As I said, the detailed outline including all the subtopics that we are going to look at in each topic is available on the NPTEL course website. So, if you need more details, please go to the website so that you can get a complete list of these topics. Alright. So, let us now move on to some other aspects of the course. Before I start the course formally, let me also give you a list of prerequisites that you need to understand the material present in this course. A list of prerequisites that I recommend. The first one is a basic course on probability and random processes. Another course that is you need some basic information or you need to know in some detail aspects of probability, especially random processes. You also need to know some basics of digital communication systems, basics of digital communication systems. An introductory, since this is an advanced course on 3G and 4G mobile communication systems, it would be good if the students are familiar at least at an introductory level with some concepts of 2G wireless systems and the development of wireless communication systems so far. So, some introductory course. So, I will write here introduction to wireless systems, and 4 a basic course on linear algebra. Alright. So, I would strongly recommend the students have a background, basic background or an undergraduate level background in these aspects, that is probability, random processes, digital communication, introduction to wireless systems and linear algebra, because this is an advanced course. So, we are going to need a background of sufficient knowledge of these fundamentals, so we can understand the material presented in the rest of this course. And however, a lot of these prerequisites are already available in the form of NPTEL courses. So, let me refer you to the relevant NPTEL courses that the students can look at before coming to this course on 3G and 4G mobile communication. So, the relevant NPTEL courses are 1. Communication engineering, the course on there is an NPTEL course on communication engineering. There is currently an NPTEL course on communication engineering, which will introduce you to aspects of probability and random process that you need for understanding communication systems. So, please refer to that course. There is another course on digital communication. This describes basic principles of digital communication systems, and there is another course or an introductory course on wireless communication. So, these 3 courses are already available on NPTEL. So, please go through these 3 courses so that you gain an understanding of the fundamentals that are required to understand the concepts that are going to be present in this course, that is advanced 3G and 4G wireless communication systems. And this course I would say is suitable for 4th year or basically 4th year undergraduate students. So, let me write this course suitable for 4th year undergraduate students or MTech students of any year and PhD students, that is, let me write MTech and PhD. So, this course is suitable for 4th year undergraduates, 4th year because you need some prerequisites in terms of basics of communication systems, digital communication, probability and random process and so on. So, it is suitable for 4th year undergraduate students and PG students, namely MTech and PhD students. So, with that, let me formally start with actually going through the course content, which is the first chapter of the course, which is wireless communication. So, let me start going through the first chapter, which is wireless communication. Let me first start with a brief description. Let me start by drawing a picture, so it becomes clear what the wireless communication environment looks like. A wireless communication system typically contains a base station. All right, let me use some color to represent this. It contains a base station that is transmitting to a mobile terminal, your mobile phone, or that is technically also known as a mobile station. So, I have a base station that is mounted typically at a very height, on a tower, on a base station tower, and a mobile station which I am going to denote as MS, all right, and there is a signal that propagates from the base station to the mobile station, that is the electromagnetic wave or the wireless signal. This information you should be familiar with, since I am assuming you have already gone through a basic introductory course on wireless communication systems. However, unlike traditional wireline communication systems, that is where the signal propagates on a wire, in a wireless communication system, since the radio environment is open, in addition to the direct propagation, that is the direct line of sight propagation between the base station and the mobile station, there are also several reflected components that arise in the environment. Namely, let us look at some scatterers in the environment, such as trees. What I am drawing here are essentially trees, and they scatter the wireless signal. There might also be other buildings in the propagation environment. There are also other buildings, because most of these are employed in urban city environments, and in such environments there are other scatter components that are reflected of cities, of buildings. And there might also be other scatterers, such as moving objects such as cars, so on, which are moving and which also scatter. So, in general, the wireless communication environment is very different from the wireline communication environment, because you not only have the direct one path between the base station and mobile station, but you also have many scattered or reflected paths, and these objects which scatter the wireless signal are known as scatterers. These are typically objects, large objects, such as, for instance, trees, cars, vehicles, large buildings. In a rural scenario, it can also be objects such as large mountains, hillocks, and so on and so forth. So, these are the scatterers, which implies at the receiver you not only have a single component, but you have multiple components, that you have the signal arriving at the mobile station through not just a single path, but multiple paths, and hence this is known as a multi-path propagation. This is known as a multi-path propagation environment, because unlike wireline channels, in a wireless system there is a direct path and there are also many scatter paths and there are multiple paths, hence this is known as a multi-path propagation environment. And there are technical names for this. The direct path is known as the LOS, or so the direct path is known as the LOS or line of sight component, and the scatter paths, that is one that is not the direct path, is known as the non line of sight or NLOS component. So, the scatter paths which are not do not arrive directly, but which arrive because of the scatters are known as NLOS or non line of sight components. So, that is the characteristic of the wireless channel, where we have the signal coming to the mobile station through multiple channels. Now, obviously, when you have such an environment, you must be familiar from a basic understanding of high school knowledge of electromagnetic waves, that each wave that comes through a different distance is subject to an attenuation because of free space losses, and also because the distance is different, the delay is different, which means the phase that it arrives with at the mobile station is different. So, we have these different signals, we have the same signal arriving at the mobile station with different paths. It is adding up at the mobile station with different attenuations and different delays. Hence, we know from a knowledge of high school physics that these signals, depending on the different delays, have a phase factor, and depending on the delays they can either add constructively to produce constructive interference, that is increase in the amplitude of the net signal, or at times they can also add destructively, that is they can cancel out each other to produce destructive interference. So, an important idea of mobile communications, let me just write the title again here. An important idea of wireless communications is multipath components add with different phase factors because of the delays and different attenuations arising because of free space losses and scattering, and hence it results in constructive or destructive. Which means if it is constructive interference, it is good because the signal level goes up, but if it is destructive interference, that is bad because the signal level goes down, and hence we are not able to receive any signal. So, that is why the wireless communication environment is an adverse environment, because multipath propagation and or rather multipath interference results in a signal level that is if there is destructive interference, then the signal level is low, in which implies that there is no reception of signal. All right. We want to model the wireless propagation environment as a system with some impulse response h of t, to which the base station inputs the signal x of t, that is, this is the signal transmitted by the base station x of t. It propagates through the wireless environment, which can be characterized as having a response h of t, and the output is the signal that is received at the mobile station, which can be denoted as y of t. So, this is the transmitted signal, x t is the transmitted signal, all right. H t is the wireless channel, and y t is the received signal. This is also often abbreviated as Tx for the transmitter, Rx for the receiver. All right. So, Tx signal denotes transmitted signal, Rx signal denotes received signal. Wireless channel has an impulse response h of t. So, when I pass x of t through h of t, the output is x of t convolved with h of t. This you should be familiar with, because you should have done a basic course. Being either a 4th year undergraduate or an MTech student, you should have done a basic course on signal and system analysis, which will introduce you to the concepts of linear time invariant systems, where x of t, if it's passed through a system with impulse response h of t, the output is y of t is x of t convolved with x of t. All right. Now, let me start with a model. Let me again redraw the basic wireless system that we had earlier, which is there is a direct line of sight component or a direct path between the base station and the mobile station, and in addition there are several scatter paths between the base station and the mobile station. Now, let us look at one such path, that is the direct path. Let us say we already said each path produces signal copy which is attenuated, such as by the free space or by the scatterers, and also is delayed. Now, we know from the theory of linear systems that an attenuation is simply a scaling of the signal, which corresponds to multiplying the signal by a scaling factor a naught, and a delay is simply corresponds to an impulse function delta t minus t naught, where t naught is the delay. So, a naught is the attenuation factor, tau naught is the corresponding delay. All right. So, the signal x of t, when it is passing for the first path, is attenuated by a 0, delayed by tau naught, as a system that can be represented as a system with impulse response a naught times delta t minus tau naught. Now, similarly, the first path here, that is, if I call this the 0th path, and which is the direct line of sight path, the first path can be characterized as some attenuation a 1 and delay tau 1, that is, it has an impulse response a 1 delta t minus tau 1. So, this is the 0th path or the line of sight path. Remember, we introduced this nomenclature, LOS stands for line of sight in the previous slide. A1 is the first path or the non line of sight path with attenuation A1 and delay tau 1, and similarly we can have a second path which has amplification A2 or attenuation A2 and delay tau 2, so on and so forth. We can have up to L paths, which is the 0th path line of sight, and L minus 1 scatter paths denoted by the L minus 1th path has an attenuation denoted by AL minus 1 and delay denoted by tau L minus 1. And now it is easy to see what the model of the wireless channel can be. It is simply a combination of all these paths, which means the wireless channel impulse response h of t, which is the impulse response of the wireless channel is simply the impulse response of the 0th path, that is A0 delta t minus tau 0 plus the impulse response of the first path, which is A1 delta t minus tau 1 plus so on until the impulse response of the L minus 1th path, that is A L minus 1 delta t minus tau L minus 1. Alright. So, the net impulse response of the system is the sum of the impulse responses corresponding to each path, which is the attenuation corresponding to that path and the delay corresponding to that path. That is, for the ith path it is A I, the attenuation A I, delay tau I, and I can represent this compactly as sigma I equals 0 to L minus 1 A I delta t minus tau I. Alright. So, the time domain impulse response of the wireless channel of this multipath wireless channel is I equals 0 to L minus 1 summation A I, where A I is the attenuation, delta tau minus tau I, where tau I is the delay. Alright. This is the impulse response of the wireless channel. Now, look at this, this summation has L components, that is I equals 0 to L minus 1. Each component arises because of one of the paths between the base station and the mobile station. Hence, each of these is known as a multipath component. So, each of these is known as a multipath component. Alright. So, each component which corresponds to a path is known as a multipath component. This channel that we have described here has L multipath components. One of them is index 0 is the line of sight component. The other ones from index 1 to L minus 1 are the non line of sight or the scatter component. Alright. So, this essentially is going to be for us the impulse response of the wireless channel. It is important to understand this because this is going to play a key role in the rest of the development. That is, the wireless channel can be represented as a sum of multipath components corresponding to the attenuation and the delay. Now, let us model the wireless signal. Let us model the wireless signal that is transmitted by the base station. Alright. So, the base station transmits a wireless signal. Let us model that signal. Let me call that signal S of t. S of t can be denoted, S of t is a passband signal, that is, it is transmitted at a carrier frequency. I can model that as the real part of SB of t times e power j 2 pi fc of t. Now, this is slightly sophisticated notion that we are using here, and that is why I assume you have had the prerequisite or you have gone through the prerequisite of communication engineering. It is important because this notation that we are using here is, it has a name, it is a very standard notation in communication systems. This is known as the passband baseband representation. This is known as, so this is known, this is a passband signal, this is the complex baseband representation of that. So, this is built on baseband, passband, the representation. All right. And in fact, SBT is known as the complex baseband equivalent of the passband signal ST. This is the complex baseband equivalent of the passband signal S of t. What is transmitted is S of t, which is a passband signal. SB of t is the complex baseband representation corresponding to this passband signal S of t. Fc is the carrier frequency. Fc is the carrier frequency. This is the baseband signal. Fc is the carrier frequency that is allocated to that particular cellular network operator. As we know, in India, there are a couple of frequencies specific allotted carrier frequencies to current systems. For instance, let me give you an idea. For current GSM systems, the allotted carrier frequency is either 900 megahertz, where each megahertz is 10 to the power of 6 hertz. So, this is 900 into 10 to the power of 6 hertz, or there is also another carrier frequency which is the 1800 megahertz carrier frequency, or it can also be represented as 1.8 gigahertz, where 1 gigahertz is 10 to the power of 9 hertz. The allotted carrier frequencies for 3G and 4G systems are 2.3 gigahertz to 2.4 gigahertz, that is 2.3 into 10 to the power of 9 hertz, or 2.3 gigahertz to 2.4 into 10 to the power of 9 hertz, or 2.4 gigahertz. So, these are the values of Fc that have been allocated specifically for GSM and 3G 4G systems, and it is important to allocate different carrier frequencies for different operators, especially because when you transmit over the air, each one needs a unique spectral band so that these signals do not interfere over there. All right. So, spectrum is an important part. So, before you transmit, the base station up converts the baseband signal to the allotted carrier frequency, and at the receiver, the mobile station down converts the received signal back to the baseband. All right. So, as we have seen so far, the transmitted signal S of t can be represented as the real part of SBT times e to the power of j 2 pi FCT, all right, and the channel, the wireless channel, can be represented as sigma I equals 0 to L minus 1 AI, that is the attenuation corresponding to the ith path, and delta tau minus tau I, where tau I is the delay. So, now what we have done is successfully we have modeled the transmitted signal by the base station and the multipath environment of the wireless channel, or the multipath propagation environment of the wireless channel. As we had said before, the received signal at the base station y of t is now simply a convolution of the transmitted signal S t with the wireless channel h of t. Now, let me do this component by component. Let us first do it for the line of sight component, that is, so the line of sight component is characterized by attenuation A naught and delay tau naught. If I pass my signal S3 through this component, as we all know from an analysis or an understanding of the basic course on signals and systems, my received signal will be attenuated by A naught and delayed by tau naught. So, corresponding to this path, the received signal is simply, let me denote that as y0 of t, which is signal ST transmitted through this component, which is real part of, now the signal is multiplied by A0, that is A0, and it is delayed by tau naught, that is the delay. So, I have SB t minus tau naught. Everyone knows if I delay a signal S b of t by tau naught, the output is S b t minus tau naught into e power j 2 pi f c t minus tau naught. All right, let me repeat this argument again, because things are starting to get a little bit complex. We are building on these notions, that is, the corresponding to the 0th component, we have the received signal y 0 of t, which is the real part of a 0 S b t, which is attenuation a 0, and S b t delayed by tau naught e power j 2 pi f c t minus tau naught, that is the carrier delayed by tau naught. Similarly, the signal corresponding to this path, to the first path, can be written as real part of now a 1 t S b t minus tau 1 e power j 2 pi f c t minus tau 1. All right, so this is the response or the output corresponding to the second path. We will stop this discussion here, this first lecture, and we have covered different aspects in this lecture, that is the family of 2G, 3G, 4G wireless communication standards, the nature of the wireless multipath propagation environment, the nature of the transmitted wireless signal, and we have started looking at the received signal at the mobile station corresponding to the transmitted signal. So, let us stop here and let us take this discussion forward in the next lecture. Thank you.